you now have the files and exercises. So just to be sure that everybody can access it, let me check the font size. Maybe a bit small, or is it okay? Do I have a magnifier on that thing? Don't think so. If I increase the font size, probably only increase that. So let me do something.
I think the console is good. It's just the browser was checking.
And it's like white on black on white. It's a bit less contrast. So it's quite easy. It's github.com, which is like this open source like distribution system. You go on my username, then it's Rosset, my full name, like concatenated, and then QISS 2019. So the URL is on the whiteboard as well, but due to the glare and light, I don't know if it's very readable. But I assume that you can connect, otherwise I'll solve it later. I'll just show you what's on that list of files. But don't worry, like if you can't get it working right now, the first exercise that we'll do through this session is going to be pen and paper. It's going to be a different thing on inflation. Then I will mention like the 3 other exercises that you can solve. It's kind of a mix and match. What I advise is that you work at least in pairs or group of 3 to 4 people, because then it's much fun to like solve problems together. And you pick like the problem that suits more your interest. So there are 3 problems you can solve on a computer. The first 4, like the first 4 file, you'll see that I have a IPyNB and a .m file. The IPyNB, if you view it on the web, it's a Jupyter notebook. It's quite a hassle to get Jupyter notebooks running with MATLAB on your own laptop, so I don't recommend that. But what I recommend is that you access the file over here. Unfortunately, I could not get like a good PDF or LaTeX export. I'll solve that later. But if you view them just on the GitHub console, you see like the command line explanation. Okay, apart this part here, it works well, and you get it over there as well. So you have the code, the explanation, and basically those exercises, they are filling the blanks. So to give you an example, here I show you how to use YALMIP, and later on there will be a bit of RepLab. Like all the instruction, all the domain-specific things they have written, you don't need to worry about. What you only need to worry about is that here, the expression for CHSH is left blank, so you need to do the right combination of monomials to complete it. And here you have a matrix. I just filled the first line, and you need to complete the remaining 4 lines. And then like you can just run the rest and see if you get the right answer. So of course, when I say run, that's imagining you would have a Python notebook. The cool thing is that there is an equivalent .m file, and the .m file is basically MATLAB code with the Python, documentation in comments. So you can just take this, cut and paste into MATLAB, and then you're good to go. If some of you are not familiar with MATLAB, then I will be available also to help you run MATLAB. In all this project, the most important thing is the first 2 lines. So they will not run as they are on your own computer. What's important is that you need to run replab add path, and the parameters should be 2 and 1, because that includes then YALMIP and SDP-tree. And then install SDP-tree so that the SDP solver is present. If you don't have that, you can only define the problem, but maybe not solve it. Again, like ask me if you have like any issues with those things. What I want to mention is really like this first line. It's made for my own computer. When I put replab in a project subdirectory, it will not be the case on your own computer. So the 3 problems are, I will start by the one that's called cut inflation. And that's exactly what we have seen on the board, not at the previous session, but the one before. So the only thing I didn't have time to do is the graph, so I just put them like with fake arrows like on a line. What you have to do is just arrange them on a cycle and loop at beta, and that's the convention that we are going to use. I decided on an order of enumeration for the vector coefficients here. And then we're going to define as well like an inflation variable. And the goal is to find or to match them using constraints. So we define the variable there, and the first constraint is very easy to do. You take that variable, you say greater or equal than 0. If it's a vector, the constraint will be vectorized. That applies to all the coefficients. But now we need to compute things like the marginal PA, the marginal PC. So I put already like the variant for those ones. PA, in the enumeration, you'll see that all these ones, they have like the A equal to 0. All these ones have A equal to 1. So if you just do the sum like this, then you get a vector with two components. That's P of A equals 0, P A equal 1. We do the same one for PA1C1, and then match the constraint here. Now your goal is going to write the constraint for AB and BC. The same story, you need to find the right matrix to put. Don't worry, at the end of the session, you'll get like fully corrected solutions. I'll give you like the MATLAB and the Jupyter notebooks. And at the end, we basically put all these constraints in a constraint array, and we optimize. Because it's a feasibility problem, we just put like optimize over the constraint. The objective is just 0, and it will tell you either successfully solved or that it's infeasible. Of course, if you just use what I've written here, it's going to be feasible because you don't have enough constraints to really say anything meaningful, but as you complete those things, you will get nice stuff. The first goal is going to reproduce, to see if we can reproduce the proof that P equal is incompatible. Then at the consistency check, I advise you to test P not equal the one where like they never output 0, 0, 0, 1, 1, 1. We know there exists a model, so this one should be compatible. And finally, there's a distribution W that's going to be interesting because you'll see something about the status with respect to the cut inflation. It will tell you something. And then one of the pen and paper problems is going to prove that the W is incompatible with the triangle, but using a different inflation. Then we move to sum of squares. So there is a variant called non-symmetric. Again, we start with like adding replab to the path. I see here that the matrix doesn't plot, which is, so this is LaTeX syntax. It's not nice for you because normally I made sure that this was like beautiful and fancy. It's not, so I will correct that and at least put it on some board if it doesn't show. We declare all the monomials. Then you have to, I said, you have to fill up this moment matrix and solve the problem. And finally, the last. So basically, each of those problems correspond to one of the sessions. And the very last one, now we use the symmetrized variant of the CHSH SOS relaxation. So we just have one variable. I didn't put like the monomial type because we know it's A0, B0, and also like all these order and that square. Of course, the objective now it's 4 times this. I put it there. No need for you to worry about it. So that works immediately out of the box. But now the question is, let's find a version of that matrix with a change of basis that's fully diagonal. And for that, we will use replab. So here you don't have much to do. What I do first is to express that matrix not with like symbolic variables, like YALMIP variables. Because the problem if I do that is that anytime you try to check a change of basis, you will just see like, symbolic matrix. It's not going to tell you what's inside. So it's very difficult to see, is it really block diagonal? So it's best actually to write the matrix as a combination of a constant and the scalar times the basis elements. And then you can check individually if the identity matrix is always going to be completely diagonal, but you just check that A is block diagonal using your change of basis. So that's cool, you can play with that. Then the only thing you have to solve is this. We have seen during the last session that the CHSH polynomial is invariant under those change of variables. And your goal is going to translate those change of variables into sign permutations. So what I did is that I put the first these two vectors, so then you can see what's the sign permutation convention used by replab. And then you have to complete the third one. And now, what I'm doing here, I'm basically using replab to compute the change of basis. I don't think in an hour and a half I can give like a complete tutorial to the software, but at least you can run like the commands that will perform that decomposition. I'll give you like a few hints right now, and then I can move through the groups to complete the details. So what we do, we have those raw vectors that represent permutations, and that's a design principle of RepLab. Most computer algebra software that you use for group theory, they will require you to use cycle notation and like extra stuff. But if you use MATLAB, you're already permuting vectors using raw vector of indices. So this is the primitive that RepLab is using here. The only addition I have here is that I allow like negative integers that represent a flip of a sign. Then I'm going to construct a group. So what I do, all the commands in RepLab, they start with the prefix RepLab. This is so that RepLab doesn't pollute the other packages that you're using. And inside RepLab, there is something called sign permutation. It's the group of all sign permutation on n elements. Here we have 5 elements. And then what we are going to ask is the subgroup generated in these curly braces. It's a cell array. So when you have an array of things that are not numbers, you put them in curly braces, and it's a bit different. So you say these are my generators. And later, when you have completed like G2 and G3, then you just replace that G1 by, so on the right here, it's going to tell you that you put just G2 and G3 on this array. Then what we do, we compute the order of the group just to check how many elements are there when we close the set under composition. And you can even explicitly enumerate them. So whatever group of permutation you're working on, you can basically check its size and enumerate the numbers. But of course, we're not studying a group of permutation. We are studying more like a representation. How does that group act on the matrices of the SDP? So what we have here is a natural representation. It means that for permutation, it's going to be permutation matrices. For sign permutation, we get sign permutation matrices. How RepLab represents representation? Basically, we know that it's a representation of a sign permutation subgroup. So there is like a property called group. And there is another series of properties called images. The thing is that all the group that we work with are finite. So every element of the group, I can write as a product of the group generators. So then if I want to see what's the image of any group element, this is something I did not give the theory of, but representation, they basically compose the same way as the group elements. So if I want to know the representation of an arbitrary group element, I first decompose that element into a product of generators, and the image under the representation is going to be the product of those images. So long story short, to specify representation, it's enough to just say what are the images of the generators of the corresponding group, which is what we got immediately by just asking for the natural rep there. Here it's just a demonstration. I can ask from the group. G, uppercase G was my group. I ask for sample uniformly. It means give me a random element from the group, but chosen at random such that that distribution is uniform. And I can ask what's the image of that element. Sometimes representation returns sparse matrices. So if we want to see the real shape, I use full just to get like this table here. And we see that my permutation that I sampled was just the permutation of the block A and B, and I get the corresponding permutation matrix. No surprises. So now the thing is we have a representation on R5. How do we decompose that representation? So there is a method on our representations called decomposition, and it returns an object that will split the representation in components. It's called isotypic component, actually. It's part of the space that transform in the same way. And inside each component, you have a certain number of copies of an irreducible representation. And this is what you get here, like it's all explained in that paragraph. But basically, those numbers are what interest us. On the right is the type of the representation. For what we do, we always are going to have real type representations. But if you have like cyclic group or something like that, you may see complex type representation. We can speak about it like after the session. And the number on the left means the multiplicity. How many copies do I have? And for SDPs, actually, you want representation to be as big as possible and the multiplicity to be as small as possible. Here what we have 3 and 2 over there. It means we have a group of a block in the future decomposition of size 3 by 3 and another block of size 2 by 2. This is what we had this morning at the tutorial. So now, okay, what I can do, this is a bit like, it's not something that's textbook, it's the way RepLab is written. When you have the decomposition, you can ask, okay, give me the representation in the basis that expresses this decomposition. It's called decomposition.rep, and then the matrix that changes the basis is U. And then you get that U. It's this matrix. So it's exactly what we have written this morning, except like for a few signs, like the sign here is minus first and then plus, but that's completely equivalent. And then what I'm doing, I'm just conjugating my basis matrices of my SDP to see what they look like in that new representation. And here what I see for C, it's like that. No surprise, it was like the identity matrix. And the second one, now I see that I have 2 blocks. Here it's 2 by 2, but I will have a 1 coming from the other matrix, and I have another block over there. Done. And then, of course, I can write the optimization problem, blah, 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 and solve it, just to check that I recover the same objective. So for the third exercise on symmetrization, there is much more new things coming in from RepLab. But you basically just find this sign permutation for the last generator, verify that you did something correct, and you just run it to the end. It's more designed explore what RepLab can do, learn about a few methods that are available, and I'm happy to answer questions even after the lab session. Any question until there? I have a question for you. Is MATLAB running on every computer here, or are there still people who have trouble launching it? Okay. I've seen that some people have a problem with the test, that they say that some 4 tests fail. So it's like a sometime failure. I know to correct it. It's because when I do this decomposition, I try to recover a solution that looks nice and with rational numbers, and I think it fails randomly on Octave. So there's a 1-line change I can do on your computer to make it behave correctly. But then the problem is that maybe you don't get bases that look as nice, but at least they are correct. So we'll check that individually. Second question, could everybody access the GitHub page? Good. So what I'm going to do now, so we took around 20 minutes to set that up. What I'm going to do now is to give you the statement for the pen and paper problem. I think we can leave that screen down, but we can turn on the light because then everybody wakes up a little bit, including me. And I can give you the spiral inflation problem, pen and paper. So small change of context, we go back to inflation. And we recall that the original graph was like this. And then the inflation that we're going to use now is going to be more complicated than the cut. The cool thing is that inflation will show a feature that works only for classical sources, classical variables. So what I'm going to do, I'm going to put actually the original graph in the middle. So that's my starting point. I put the original triangle there. Of course, if I want to preserve the property that is quantum, I can't clone things. So then I can't add things to this graph. It's already exactly equal to the original one. So what I'm going to do, I'm going to make copies of this variable there, which is again something that's only going to work for classical information. And I'm going to add a variant of Charlie. I'm going to add a variant of Bob. And I'm going to add a variant of Alice here. And of course, I need to connect C2. It's a bit boring to go back to the original graph. So what I'm going to do, I'm going to make a copy of alpha. I'm going to make a copy of gamma. And I'm going here to make a copy of beta. So this inflation is called the spiral inflation. It's in it's actually in Ellie's Wolf paper that I've given you. The convention will not be exactly the same. So I use something that's consistent with what we have seen before in the lecture. And now we are going to test the W distribution. So the W distribution is called this way because it's similar to a class of pure states that are called the W states, but it's something completely classical, just in pairation that the name comes from. So my P of ABC is going to be 1/3 if A plus B plus C equal 1. Okay, and A, B, C are equal to 0 or 1. So that means that exactly one of them is equal to 1, and 0 otherwise. So it means that here I have the patterns, the following patterns are allowed: 0, 0, 1, 0, 1, 0, 1, 0, 0. And this is what we are going to use. So I'm going to give you like the steps of the proof and then let you think a little bit about it. So my first question is that what happens when, so of course, there is a game of, actually no, this is not the first thing you should do. Let me remove that. First thing is identify compatible subgraph. Second question is what happens when A2 or B2 or C2 is equal to 1. So for each of these conditions, there should be a consequence. And then the question 3 is what's the probability of A2 equal B2 equal C2 equal 1? And the fourth question is, can you show incompatibility? A contradiction. Actually, the answer is yes, you should find a contradiction there. It works exactly the same way. So when we have done the cut inflation and we show that this should be equal to that, this should be equal to that, and then those two things should be blah, blah, blah. But here the logical argument is going to be slightly different. But if you follow these steps, you should find it. I think that's good. We can start. So I suggest that everybody starts with the inflation problem, and then like you can branch out to the computer stuff. And what I'll do, so now we can distribute the chocolates, because I forgot to do that at the previous session. Unlike I would say that like the first group that solved the problem will get their pick here, and then the group that solved afterward can get what remains in the box. Unfortunately, there is not enough for like everybody because it's like what we do, we select a subset of those parties, and we have 6 parties. Actually, it means that we could actually pick 64 combinations for each of the 6. I take it or I don't take it. Luckily, we have a few rules that enable us to kind of shortcut the 64 combination we can try. For example, if we found that a subset is incompatible, every larger subset that includes this one will be incompatible as well. And conversely, if I find that a subset is compatible, any smaller thing inside will be compatible as well, but they're kind of useless because they're already included in the bigger scheme. So now I'm going to tell you at least like the one that I know of. So, and I did not finish the rules. So the rules are you take the subset, you remove all the other triangles that you did not pick. And then you discard as well like the sources that are not connected to anything. To give you an example, if I keep only B2, I would discard all the other triangles. And for example, this beta will not be connected, this alpha is not connected, so I remove them. Actually, those hidden variables, they don't matter so much. They only matter in the way they connect things, because we don't observe them. So when I remove all of that, I will keep only B2, alpha 1, gamma 2. Then I look at the graph that remains, and I see if it's disconnected. If I have disconnected parts, it means my distribution is going to be a product, and now I can study the products one by one. And then for each of the components in this subgraph, what I do is I remove the labels. The first thing that I check is that I don't have two copies of the same party, because I only have one Alice, one Bob, one Charlie in the original. The second thing that I'm doing is that after I remove these labels, I check if what I have corresponds to a subgraph of this. So let's see what happens if I keep B2. I have gamma. After having used that rule, I have gamma, triangle, alpha. And that thing in blue now corresponds exactly to gamma B alpha. So this is compatible. So now what I will do is just enumerate those subgraphs and then give you the solution to the problem. So we have A to B1, but actually somebody remarked that if I include C2 as well, what happens is that I can remove this one, and then I get two parts that are disconnected. I can walk through them. Actually, for the proof, I don't need A to B1, C2, so I'm just going to keep A to B1. But if I have A to B1, then this scenario is very symmetric. I will have B2 C1 as well and C2 A1 through the same arguments. I'm just not going to put the colors because this will become a mess if I do that. But by symmetry, we see that it works. I will use other colors for the rest, so red and green. The other thing, of course, is that the central triangle is fully compatible with the original one, the same thing. And the last thing that's less obvious, but it's really fun, is that if you take only the external things, they are compatible as well, because once you remove the center, they become disconnected, and each of them is compatible. So now are we ready for the proof? How much time do we have? Oh, it's fine, still 20 minutes. So the thing is, I'll take just one of them. B2 C1 should be equivalent to BC in the original one. What we recall is that in the original one, this is A, B, C, what I have is 0, 1, 1, 0, or 0, 0. So now what I'm going to look at is what happens when B2 is equal to 1. B2 is equal to 1, then I can conclude that C1 is equal to 0. I have no other choice. If when B2 was equal to 1, C1 could be equal to 1, it means that the marginal BC could contain the correlation 1, 1, which does not appear. And by the same conclusion, I will see that, so B and B2, C1, C2, and C2 is equal to 1, then A1 has to be equal to 0. Finally, when A2, another compatible subgraph, AB, when A2 is equal to 1, that implies that B1 is equal to 0. That's the setup. Now, look at what we have on the left. B2, A2, C2. And we know that this is something that's compatible with the original graph. In particular, we know, okay, this is not a good angle. Maybe, what can I erase? I'm going to erase that on the left, because you're going to have this anyway through the, and beta 2 was there. So in the inflation, what's the probability of A2, B2, C2? We see that when we remove the central triangle, they become uncorrelated, so they become equal to the product distribution and this, each of them individually, they are compatible. So I now have PW, the original one, PW, B2, PW, C2. Now if I look at the marginal of, let's say, just P of A is equal to 1, okay. P of A equal 1 has probability 1/3. And PA equal to 0 has probability 2/3. So now the probability of A2, B2, C2, each, okay, this is bad. Let's continue here. So now the probability of, in the inflation, having E2 equal to B2 equal to C2 equal to 1, this is 1/3 times 1/3 times 1/3, this is 1/27. It's a small number, but it's still something. But then I know, like, with probability 1 over 27, I have this. So then it means that with probability 1 over 27 at least, I get that. So now I know in my inflation, so this implies, and now this starts to be busy, and I don't like writing like implication to the ceiling, but this is kind of what I have to do. I know that in my inflation, A1, B1, C1, all equal to 0, has a probability at least of 1 over 27. The thing is that it could be equal to 0 due to other things, but at least I know when this is true, 1 over 27, then this will happen. So this at least has to be 1 over 27. But the thing is that A1, B1, C1 in the middle match the original distribution. Matches. And I don't have 0, 0, 0 as something that's allowed. Contradiction. So for that, what did I need in that graph? I needed compatibility of the inside triangle. I needed compatibility of the outside triangles. And I needed like these 2, 2, and 2 to get this implication over there. So this is, let me check. I will give you the reference of that paper. So this is available in the paper on the archive. It's 1609 00672. Let me give you not an introduction to the paper, but just show you how it looks like. It's a very long paper. Oh no, 46 pages. And the problem is that it's going to describe exactly what it means to make an inflation, what it means to be a compatible subgraph, and so on. So that requires a lot of setup. What I suggest is that you skip all of that and you go directly to page 9, where you have incompatibility of perfect three-way correlation with the triangle. That's what we did with the cut. And then you have incompatibility of the W type with the triangle, which is what we just did. And if you need like a more complete reference, you at least understand these 2 examples, and now you can branch out from this part to the rest of the paper. I don't know if there are remaining questions. If not, we'll move to the second part of those exercises. You can play a little bit with MATLAB and so on. And in like 10 to 15 minutes, I'll give like a correction on the computer. And I see that this mic is now on the ground, so I think part of it has been lost in the recording. I'm sorry. So what you're going to get in the correction, because I think there is no time to really correct them. The cut inflation, I had the matrices that define the marginal. It was basically summing the right coefficients, so I would get the variable A, B, A, C, and so on. In the correction, what you have is which matrices you should put there. And they have a very regular structure because they sum over the corresponding coefficients. And what happens if I run actually that script? So then I need to go to QISS 2019. If I run this cut inflation correction, hey, wait a minute. Oh, it's like this. Cut inflation. Check. So what it's going to tell me at the end, infeasible problem. So that means if I try to, oh, wait a minute. So that means if I try to check if the GHZ distribution is compatible, MATLAB, okay, like it's written in this crappy yellow. MATLAB is telling me this distribution is incompatible. And then I can test like other distribution, and you can play with it there in the file, and you will see that the other 2 are compatible. The not equal, we have seen there is a model, it's compatible. And the W is compatible with the cut, because this file is for the cut inflation, but we have seen that with the spiral, it stops being compatible. So with that, we have discovered that to test distribution, sometimes we need to switch to different inflation and get like more and more complicated ones. I don't think I have time to go in detail on the SDP SOS stuff. So what I advise that you look at these files, if that's your domain of interest, anytime you want to work on them, you have those files. They will be helpful to work on papers because I don't think there exist on the web kind of basic examples of SDPs for quantum. So they're a nice set of starting examples. And as I said, I'm here until Thursday, so actually until the weekend. So anytime during the conference, ask me a question about those methods, what you could use them for, and so on. That said, I want to thank you for your participation because I think it really went well. I really enjoyed giving like those 3 lectures in this lab session. Even if it's actually we covered a lot of information. So I think if you want to work on these fields now, you have like basically what's like a good starter kit. I'm very happy what we could cover. Thank you.
Thank you.